So this video is basically going to talk about a little bit more on Extrema and some optimization problems. And my goal is that by the end of this video, you'll have an understanding of how to use the second derivative test to locate Extrema, and also how to use basically what we've been doing with derivatives to apply to real world applications. Okay, so we're going to go ahead and get started. Now, you have seen how we use the second derivative to determine concavity and inflection points for a graph of a function. Well, the second derivative can also be used to find extrema, and this is called your second derivative test, which basically says that if the derivative at a particular point is equal to 0, and if a second derivative exists, then there are three basically possible conditions that could happen. If the second derivative at a point is greater than 0, then f has a relative minimum at that c, at that x equals c value. If the second derivative at c is less than 0, then f has a relative maximum at x equals c. And lastly, if the second derivative at c equals 0, then the second derivative test fails and the first derivative test must be used to locate relative extrema. So in other words, the second derivative test, again, is basically helpful to find relative maximum and minimum. However, there is a possibility that you can't use the second derivative test to find those relative extrema. So in that case, you'll have to use the first derivative test. Can you use the first derivative test just anyway without having to use the second derivative test? Of course you can. However, there might be situations where it might be easier to use the second derivative test instead of using the first derivative test to find your extrema. So what we're going to do, oops, I forgot to clear off this page. So what we're going to do is we're going to actually take a look at an example here, and you're going to use the second derivative test to find relative extrema, if it's possible. Okay, so here we go. All right, so it says use the second derivative test to determine whether or not we have extrema. So in order to use the second derivative test, we have to find what the second derivative is. So what we're going to do is we're going to do exactly that. We're going to find the second derivative of these functions here. And I apologize, I'm having some issue with my pen and my board. Okay, so let's find the first derivative. So, first derivative, here's a working pen. Using the power rule, is 3x squared minus 3x. The second derivative is 6x squared minus 3. I'm sorry, 6x minus 3. I wrote it right, just didn't say it right. Let's try this again. 3x squared minus 6x is my derivative, and then 6x minus 6 is my second derivative. Okay? So that's what the first thing we have to do is find those, and then what we're going to do is we're going to set our first derivative equal to 0 and solve for x. Okay? Because by doing this, we'll basically be able to find those critical points and then use the second derivative, use those points to plug into our second derivative, okay? So we know that there's an x in common, and actually there's also 3 in common, so let me fix that, okay? So I'm solving for x, so I'll look for my greatest common factor, so that's 3x. That leaves me with the x minus 2. Set both factors equal to 0, and I see that x equals 0 and x equals 2 are my critical points, okay? Those basically represent the c that I'm basically going to test in my second derivative test, okay? So I'm going to go ahead and I'm going to plug in 0 into my second derivative, and I'm going to plug in 2 into my second derivative, okay? So when I plug in 0, I get a negative 6. When I plug in 2, I get a positive 6. Okay? Now, according to the second derivative test, it says that if you plug in, if you do f double prime of C is greater than 0, then we know we have a relative minimum. If it's less than 0, we have a relative maximum at these particular points. So, since this is negative, whenever I plug in 0, that means that I have a maximum at 0, comma, whatever. And since at 2 I have a positive 6, that means I have a minimum at 2. Okay? So, all I have to do is figure out the corresponding y value that goes along with those particular points. So, basically what I do is I take 0 and I'm going to plug it back into my original function to find the corresponding y value. Okay? So f of 0 equals 0 minus 0 minus 2. So I have a maximum at 0, negative 2. And then to find my minimum, I'm going to plug in 2. So I'll get 8 minus 3 times 4 minus 2. Let's see, that's 8 minus 12 minus 2, negative 6. So then there is my minimum. All right? So again, we use the second derivative test to determine whether or not we have extrema and where it's actually located. So to do that, we take our first derivative, set it equal to 0, find our critical points, and then we plug those points into our second derivative to see if we have a max or a min. Okay? So let's try B. All right? We need our first derivative, which is going to be 15x to the 4th minus 15x squared. And I need my second derivative, which is going to be 60x cubed minus 30x. Okay? Both of these can be done without a calculator, so don't think you got to pull out your calculator here. Okay, you can do it. So now we're going to set our first derivative equal to 0, just like we did last time, and solve. Well, we have a greatest common factor of 15x squared, leaving us with an x squared minus 1. We're going to set both factors equal to 0. And we see that x equals 0, and then x is going to equal a plus or minus 1. Okay? So in this case, we're going to have 3 critical points that we're going to test. So now we're going to plug each one of those into our second derivative. And we're going to see where we're going to have some relative min and some relative max. Now when I plug in 0 into the second derivative, I get 0. When I plug in 1, I get 30. And when I plug in negative 1, I get negative 30. Okay? At any point in time in this video, if you want to try a problem out, you can always pause it and then press play whenever you're ready to see how well you did. Now, according to the second derivative test, it says that if f double prime of c equals 0, then the second derivative test fails, and we'll have to use the first derivative to locate relative extrema. Okay? So if you look, the first one, when I plug in 0, equals 0. So that means I can't use the second derivative test. Now, if this was my only 0, then I would have to default back to the first derivative. However, I have two other equations that I had a critical points to plug into, and they actually do give me some relative extrema. Okay? So because this one is positive, since this one is greater than 0, that means there is a minimum at 1. And because this one is negative, it's less than 0, that means there's a max at negative 1. What are those specific points exactly? Well, again, you go back and you plug it into the original problem. You do f of 1, and then you do f of negative 1. So when I plug in 1, I'm going to get a 2. And then when I plug in, negative 2. And then when I plug in negative 1, I get a positive 2. So that means my minimum occurs at 1, negative 2, and my max occurs at negative 1, 2. Now what I want you to do is I want you to try this problem on your own first. So pause the video, and then when you're ready, press play to check your answer. Okay, so hopefully you pause the video so that way you can try this out. What I did to find the first derivative, I did a chain rule. You could have FOILed it out and gotten the same remotely the same thing. But in the end, we still would have gotten the same critical points. But I used some of our rules. So I did chain rule first, and I got 4x times the quantity x squared minus 1. And then I did the second derivative using the product rule. First times the derivative of the second, plus the second times the derivative of the first. And then I simplified to get 12x squared minus 4. So after you do that, remember you set your first derivative equal to 0, and you solve. So I got 0, 1, and negative 1. Then you plug it into your second derivative, as you see over here in the blue. And you'll see that you have negative 4, you'll have 8. Sorry, let me fix this. You have negative 4, which is less than 0, 8, which is greater than 0, and 8, which is greater than 0. So if it's less than 0, again, looking at the test, if it's less than 0, that means there's a maximum, okay? So there's going to be a maximum at 0, and there's going to be 2 minimums, okay? 2 minimums. So we have a max at 0 comma something, and we have a min at 1 comma something, and negative 1 comma something. How do we find those somethings? We plug them back into the original. So when I plug in 0, negative 1 squared is 1. When I plug in positive 1, I get 0. And then when I plug in negative 1, I'll get 0. Okay? So then there are my max and my mins. Now, you have absolute extrema are the greatest and the least values of the function over an entire domain. Absolute extrema occurs at either the relative extrema or at the endpoints of a function. Now, everything we talked about up to here was relative maximums and minimums, but now we're going to be talking about the absolute, basically the highest possible maximum of the entire function or the lowest possible point on the whole curve, okay? So we look at this diagram we have here, we have an example, okay? This point right here is a relative minimum because clearly there's another point that's lower than it. So this point would be your absolute maximum. Here you have a relative maximum because it's not the highest point that you can go. That one over there is an absolute maximum. So when we look at an example, it says identify each labeled point as an absolute max or min, a relative max or min, or neither, okay? So right here, A and F, they do represent endpoints, and so A would be our absolute maximum because this is the highest point amongst the entire curve. C would be relative max, E would be relative, and F, the truth of the matter is that F is an endpoint. However, it's not our absolute endpoint, and so in that case, this would be neither absolute or relative, okay? The only time that a neither would occur is if we're looking at an endpoint. Down here, B, this is a relative minimum. D, the first D, I just noticed that there were two. Let's go ahead, let's make this one a G. But this D, okay, this is an absolute minimum because it's the lowest point on the curve, and then G would be another relative minimum. So you can have multiple relative mins and max, but you only have one absolute max and one absolute min. All right? Now let's take a look at this equation here that says find the absolute maximum and minimum for this function, okay? So what we're going to do is we're basically going to take our first derivative, all right? And we're going to set our first derivative equal to 0, okay? Because when we do that, we're going to find our critical numbers. And remember, our critical numbers is that basically means there's a max or a min at that number, okay? But the truth of the matter is we're trying to see if it's an absolute max or an absolute min. So we're going to take our first derivative, set it equal to 0. So that's going to be 2x minus 2 equal to 0. 2x equals 2, x equals 1. Okay, so that's my critical point. Now, I want to see exactly what's happening at 1. So what I'm going to do is I'm going to plug I'm going to plug 1 into my original function. So I get 1 squared minus 2 times 1, which is a negative 1. All right? Now, I also have to take something else into consideration, are these endpoints, okay? Because we're only concerned for this function from negative 1 to 2. So negative 1 and 2 are my endpoints, which I need to test as well. If you recall from the last diagram, remember we were able to label our endpoints as well, okay? So we have to test them. When I plug in negative 1 into my original function, I'm going to get positive 1 plus 2, which is 3. And when I plug in 2, I'm going to get 4 minus 4, which is 0. So just by looking at this, I can actually see where my absolute maximums and minimums are. Okay? Since 3 is the highest value I have, that means there is an absolute maximum that occurs there. And since this negative 1 is my lowest value out of the 3, that means I have an absolute minimum. Okay? And those are actually my specific y values that represent those absolute maxes and mins. So my absolute minimum occurs at 1, negative 1, and my absolute max occurs as negative 1, 3. Okay? I don't know if I have another, yeah, okay? So if you have any questions, let me know. I'm going to have another video to represent for our optimization problems.